So again, this document here is in our D2L folder. So you can get this off of our D2L class. That's the link there to vote if you have preferences of what I cover in today's class. So today is a bit more of a guided review. In your recitation tomorrow, it's a little bit less formal. You can come and ask questions and all that sort of stuff. Of course, there still are, roughly 30, 35 students, in each recitation. So the recitation instructors will not be able to cover every question out there. And so, certainly do bring some questions for them, and they'll have some backup questions as well. But if you can't get your question answered in recitation, certainly post it on Piazza or come to my office hours or go to the MLC, or there are other opportunities for you to get your questions answered. But hopefully we can get a good sampler platter of the different problems here. All right, so while you're doing that, let me do the last iteration of, or the last chance of some administrative announcements. The big thing, is that our test is tomorrow. That's from 7 to 9. It's a 60-minute long test. There's we already pointed out the exam and quiz revision assignments. Those are a good way to study. Of course, going back and reviewing your web work homework, that's a good way to study. We also talked a little bit about, in my folder here, I have a checklist. So a test or a skills checklist, which you can go through and kind of look at what are the big things that you should be able to do from each section. So for instance, we could look at 12.5. 12.5 was a very large section, with many types of problems. But the key things are, if you have 2 points, you should be able to find a line. If you have 3 points, you should be able to find a plane. Certainly had examples of that in the web work homework. Calculate when lines or planes intersect. So if it's lines, you have to find the t value. If it's planes, you're going to get a line of intersection. Calculate angle of intersection between lines and planes, and calculate distance between lines and planes, So those are the key things that walking into the test tomorrow, walking into the test, loading the test on your computer tomorrow, These are the key things that you should be able to do from 12.5. And you can kind of go through there and see and verify, hopefully in each section, that you're relatively happy with all of the main topics that should be covered by our test. All right, I think that's all of my admin stuff that I wanted to make sure that I covered. Questions, though? Any questions? Okay. Well, I will be going to this link and seeing the results here in just a second. And I'll try to identify a few problems for us to start with. But I will also revisit this. So if you haven't had a chance to vote yet, you can still get your vote in, and I'll, again, use these to kind of help guide and figure out which problems we should do and cover in class here in our 50 minutes together. And of course, just like always, if I can't get to the problem in class, I will post the solutions on D2L after class. So you'll get the solutions really to all of these, either through the in-class stuff or afterwards. So, okay, I think I had this pulled up right here. I need it to refresh. Okay, and so far we have 22 responses, 23 responses, and it looks like the #1 problem that folks are interested in seeing as of right now, anyway, is problem number 8, and second is problem number 6. So why don't we do problem number 8 first, then problem number 6, and then I'll revisit this page and see kind of what problems are in the lead after that, and then we'll go to those. So problem number 8 first, and then problem number 6. All right, so in this one, we want to find parametric equations for a tangent line. We're given some interesting vector function here. We have a point that we'd like it to go through. And then the question is, basically, once you have that tangent line, to do something with it. In this case, we want to get a number, and that number should be the value of x when the tangent line crosses the YZ plane. So, again, first step here is really to get that tangent line equation. So tangent lines, just like all lines, are made up of two pieces, right? There is a vector, a direction vector, and then there's a point that the line contains. Now, back in 12.5, we probably would have called this thing R of t. However, this problem here already has an R, right? An R of t here. So I'm going to use L for line. So this is going to be my tangent line here. Now notice that this already mentions the point that I would like it to contain, right? This tangent line should be going through the point 5, 6, 0. And so that right there is going to be my R naught. So I guess technically half of this is now solved. 5, 6, 0. Remember, this R naught is the vector that corresponds with this point. So I'm going to use the angled brackets, right? Because we're going to be adding it and all that sort of stuff here in just a second. Now we still have to figure out what is this tangent vector, right? That V there is normally the direction vector for the line. This is supposed to be the tangent line. So the special thing about the tangent line is that it's supposed to be tangent to the curve. So if you remember from 13.2, we found out that the tangent vector to some vector function is again the derivative, just like it was in calculus 1. So we now need to do a derivative and plug in some special time, right? Hopefully it's supposed to be the tangent vector when we're at this point. So that A there is that special time of when we are at that point. So maybe as a good first step, I could go ahead and calculate out my derivative. So R prime of t over here. And then I'm going to have to plug in some special time to say that I want the tangent vector not just along the curve and in general, but I want it at a specific point in space. So, okay, let's go through here. The derivative of 3 is 0. The derivative of E is itself. That 2 there's along for the ride. So there's the derivative of my first component. For the second component, okay, the derivative of 6 is 0. That's nice. But notice I do have a product here. I have 3t, and then I have e to the t. So when I take the derivative, I have to use the product rule. So I'm going to do the derivative of the first times the second plus the first times the derivative of the second. And again, the derivative of e is itself. So I'm thinking about this as my first function is 3t, and my second function is e to the t. So then apply the product rule to that piece. And it looks like we need to do this one more time because again, we have t times something. But now it gets even more complicated because this isn't just e to the t, right? There's also a chain rule going on because we have an e to the negative t squared. But again, same process. So I'm going to do the derivative of the first times the second. So the derivative of t is 1. Leave the second one alone for now. Plus the first times the derivative of the second. So this is where I'm going to need to use my chain rule. So my chain rule is, right, take the derivative of e, leave the inside alone. So the derivative of e is itself. Leave the inside alone for now. Then multiply by the derivative of the inside. So what's inside of e? Well, negative t squared. So when I say derivative of the inside, I mean the derivative of negative t squared. So that's going to be what? Negative 2t. So just be a little bit careful. Take your time with these things, right? And you can get it. So now the last bit is I need to plug in some special time that corresponds to, right, I want the tangent vector at a specific point in space. I want it when I'm at 5, 6, 0. So the question is, at what time value am I at this point? And so for that, right, I need to go back to my original equation here, because remember, we have our x component, our y component, and our z component. And after all, this is an x, y, z triple. And I need to figure out what should t be in order to achieve 5 for x, 6 for y, and 0 for z. And this is typically a little bit of guess and check, right? But we don't usually make it completely crazy or, super difficult, because the point of this is not, our class is not supposed to be a very difficult algebra class. The point of our class is the calculus, right? And so quite often you can kind of look at these and again, do a little bit of guess and check. So can anyone see what's the answer here? 0, right? So if you plug in 0, e to the 0 is 1. So in your first component, you get 3 plus 2 times 1, right? So that's 5, check. And you can double check, right? If you plug in 0 for t, you get 6 for y. And if you plug in 0 for t, you get 0 for z. So yes, when t is equal to 0, that's when I'm at this special point. So because I want my tangent vector at the special point, I want r prime of 0. All right, I see a hand raised here. So yeah, question.
Not the when calculating, right?
No, because there the components are x prime, y prime, z prime, right? You've taken the derivative of all of these things. So, and you're not given that information, right? We don't know what those derivatives are yet, but we do know that x is supposed to be 0, y is supposed to be 6, and z is supposed to, sorry, x is supposed to be 5, y is supposed to be 6, z is supposed to be 0. So that's why you need to use the original instead of the derivative. Good question. Okay, now I can plug in my special time and figure out what way is the curve headed, right? What is the direction of the curve at that time? So when I plug in 0, I'm going to get what, 2? I'm going to have what, 3 times 1 plus 0 times, I guess, who cares? And then let's see, I'm going to have 1 plus, and again, I'm plugging in 0 everywhere I see a t. So I get 0 times a whole bunch of stuff there at the end. And so it looks like my direction vector is going to be 2, 3, 1. So when time is 0, the curve is headed in this direction. So this right here ought to be my direction vector for my tangent line. So this is a perfectly good tangent line equation. Again, it should be a line. I've seen some posts on Piazza and stuff like this where people tell me that their tangent line has like t squared in it, or their tangent line has like the square root of t. That should be rather concerning to you, right? Because that means it's not a line. Lines should always be linear, right? They should have t to the first power, but you shouldn't see t squared or t cubed or things like this. Otherwise, it's not a line, right? You're going to have maybe a cubic or some square root thing, right? But it's not a line. If we'd like to, we can simplify this down a little bit, right? And gather all of the components, right? So if I do my scalar multiplication through by t, and then I do my vector addition, I can make this look like 2t plus 5, 3t plus 6, and then 1t plus 0. So that's maybe as clean as I can get this to look as far as my line. And again, you see all of these are very linear, right? I don't have t squared or square root of t or thing like this, right? It's just t to the first powers. Everything's a nice line equation here. So, if I was making this an exam problem, this part right here, let's assume that it's a 10-point problem. This part right here, to get to the tangent line, I would say is probably worth 8 out of the 10 points. It's worth, the majority of the partial credit. The last bit here is, right, well, we need some answer to plug into D2L, right, some number, right? And so we need to somehow turn this into a number that maybe D2L can check for us, something like this, right? So even if you don't know how to do the last bit, still do all of this, right? This is kind of very straightforward, I think. It's kind of the problems that you've seen on web work and things like this. Do all this, and then skip and maybe come back later. But even if you don't come back, right, again, take the 8 out of 10. Don't take 0 out of 10 because you don't understand the last bit. Okay, but let's solve this one all the way through. Again, the question is, what is the value of x when the tangent line crosses the xy plane? So the question is, I need an x equals something. And it's supposed to be with the tangent line. So I'm staring at really my x component, right? This is my x for my tangent line. But I need to know what to plug in for t, right? And so that's where this, okay, when it crosses the xy plane. So I want to figure out what is the time value where it crosses the xz plane. And if I know that, then I can plug in that special time here and I can get my x value. So xz plane, what is the equation of this? What is the math that's related to xz plane? Yeah, over here? Y equals 0. Yes, absolutely. So xz plane, the mathematical equation for this is y equals 0. So we want to know when y equals 0. Well, we have a y, right? This is when our tangent line is doing things. Here's its y component. So we want the y component to equal 0. That's when it's going to cross the xz plane, when its y value is 0. So that means, well, we can almost guess this one, but you can kind of move these around very formally here and get that t is going to be equal to -2. So at a time value of -2, that's when it crosses. Now it asks, what is the value of x when we're crossing here? So, okay, we have this now, this good t value, and we could plug that in, and we're going to get what? X is equal to -4 plus 5. So x is going to be equal to 1. So the final answer, the thing that I would input into D2L, if this was a test question or whatnot, would be x equals 1. But this is, this wouldn't be reasonable for a multiple choice or true false style question, right? There's a lot of work that went behind this, right? So this would be, again, I think it would be most reasonable as a standard response style question. And again, even if you don't know how to interpret this last bit, take the 8 out of 10 or so and make sure that you do the full tangent line. That's the standard thing here. And that's where all the calculus is, right? The derivatives and understanding what to plug in where, right? That's all of the calculus. So really, that should be worth the majority of the points. All right, questions on this one before we move on to number 6. Yeah, down here.
We have to say like x equals like 2t plus 5. Do we have to do that?
So the question was, I thought for parametric equations, you had to do like x equals something, y equals something, z equals something, right? And yeah, so if it did want, I guess part of this is find parametric equations to the tangent line. Of course, we end up using those. But yeah, you're right, kind of as an intermediate step here, I probably should do x is equal to 2t plus 5, y is equal to 3t plus 6, and z is equal to t. So it does say to find those explicitly. So yeah, of course, in web work, they just have the boxes, right? So fine, you can give me 7.5 instead of the 8, right? You can make me down a little bit. Good. Any other questions on this one? All right, well, let's move on to 6, and then we'll go back and see kind of what's next as far as what we should be doing. So find a vector function that represents the curve of intersection for these surfaces. I guess I should mention here, this question here comes from 13.2. So if you want to find more questions like that, you should go to the web work homework or you could go into the textbook, right, in 13.2. This one right here is technically from 13.1. When we were finding curves of intersection. So we have a couple surfaces here, and we need to find the curve of intersection for the cylinder and this interesting surface, z equals x times y. Now these ones in general, right, it is hard to find a method that will solve and find you curves of intersection for every type of two surfaces out there, sort of deal. So the ones that we do in the web work in the class and on the quiz and the exams, right, they're very kind of hand selected in order to make them reasonable to be done in a time setting. And so again, kind of this one, we have here x squared plus y squared equals 25 and z equals x times y. And the first question that I told you, I think a reasonable way to solve these types of problems that we see in our class is trying to figure out, is this going to be a closed curve or not? If it's a closed curve, remember from class, we talked about how you should use sines and cosines in that case. And if it's not a closed curve, I guess you could say an open curve, then you should try either x equals t, or y equals t, or z equals t. So this was the method that we talked about in class. So the fact that I see a cylinder, x squared plus y squared equals 25, and again, that's not equal to z or anything like this. At maximum, it's supposed to be 25. That means that really our x's and our y's are going to be at most 5 or -5, right? They're not wandering too far. So I think that this is going to be a closed curve here, which again, closed curve just means that it doesn't go on forever. Like it's some sort of circle or an ellipse or something like this. And in fact, I mean, we have x squared plus y squared is like our good old circle equation back in 2D. Now, again, it's a cylinder because we're in 3D. But so it seems likely that this is going to be closed. So when I read this, I'm thinking more about the sines and cosines. So in this case, right, I would probably start off here with x is equal to cosine and y is equal to sine. And again, the reason why I'm doing this is because these are the variables here that are involved in x squared plus y squared should be equal to 25. So again, I'm trying to find some parameterization, some set of x equals something with t's, y equals something with t's, z equals something with t's that satisfy both equations. And this says here that I should think about sines and cosines. Now I chose x equals cosine. I could have chosen x equals sine, by the way, but x equals cosine makes sense just because it kind of comes from our polar stuff, right? Back from calculus 2, we learned about how x, in polar should be r cosine t and y should be r sine t, right? So it kind of makes sense to maybe have x being cosine and y being sine. But this gets me to the next point, right? Even though you start off and you're thinking about, I'm going to be using sines and cosines, that's not where you necessarily stop, right? The answer isn't always going to be just cosine or just sine. You may need extra pieces. And in particular, because of the 25 over there, you are going to need to modify these a little bit and put some 5s here. Now let's verify that this at least is on our cylinder, right? So we're going to go ahead and do a check really quick. So if I take my x, 5 cosine t, square that, and I add it to my y squared, which was 5 sine t, if I want it to be on the cylinder, it needs to be equal to 25. If it's not equal to 25, then it's not on the cylinder, and therefore it's not on this curve of intersection, right? Because the curve of intersection needs to be on both the cylinder and this other surface. So as we expand out, we get to 25 cosine squared t plus 25 sine squared t. And you can factor out that 25. And of course, cosine squared plus sine squared is always equal to 1, no matter what t is. T could be 3, t could be 2 pi, t could be whatever. Cosine squared plus sine squared is always 1, no matter what the t value is there. So yes, this is in fact equal to 25. So we've got 2 out of the 3 then, right? We have an x and we have a y, but still the question is, what is z, right? Because in order to get my vector function, I need all 3. Well, we have this other equation here, and this says that z is supposed to be equal to whatever x is times whatever y is. So since we now know what x and y are, we can go ahead and plug those things in. So x is supposed to be 5 cosine t. Y is supposed to be 5 sine t. So if you want a simplified answer, right, this would be 25 cosine sine. This is my set of parametric equations right here. I suppose it wants a vector function r of t. And so we would go ahead and write this with our x component, our y component, and our z component. And although it's not necessary here, this is a correct answer. It is nice just to kind of get in this habit, as we progress on for chapter 16, right, to be counting each point once and only once. So I want to go around the circle once, but I don't want to double or triple count my points or anything like that. So I'll include here t ranges from 0 to 2 pi. So this right here would be my final answer. I'll go here and then there, and yeah. Great question. Yeah. So the question was, instead of 5 cosine t or 5 sine t, what if someone else chose -5 here? Or maybe you have a negative in both, right? And I think maybe why you're pointing this out is because, of course, when you take something negative and you square it, that will force it to be positive, right? So even if there's a negative there, this will still work, right? The only difference then would still be in your x, but also this is going to trickle down to your z as well. right? So then your final answer here would be negative 25 cosine sine. And so your answer would look like this. This is also a correct answer. So yes, just like when we were in 12.5, I told you there are infinitely many correct ways to parameterize a line. And sometimes you can have two different parameterizations and they actually are talking about the same line. Same thing is true for more complicated curves as well, right? Lines are kind of the easiest. And so if there's already infinitely many parameterizations for a line, you know there's going to be infinitely many parameterizations for everything else. So this is another parameterization that is completely fine. Likewise, you could have switched the sines and the cosines, right? Actually, the x could be sine and the y could be cosine, and that would also work out perfectly fine. So these are different parameterizations, but they all map the same curve. They all map to this curve of intersection. So back here, and then we'll come up here. Yeah.
Like steps you can get there, but how do you know that like that's your final equation, that that's like the equation of the curve? What is like that curve?
Yeah. So this is going to be, it's part of this cylinder, but it's going to be slanted. It's not even quite an ellipse. It's kind of, it's stretched out because this x times y has some curvature to it. It's not just a plane. So if I was to draw this, it would look something, I don't know, like this sort of deal, I would guess. It would look something like this. So it is closed, and it does go around with the x and the y here, but it's kind of stretched, interestingly, in the z direction a bit. So you know that this is the curve of intersection because it needs to satisfy both surfaces. If it is on both surfaces, then that means it is the curve of intersection. So when I go ahead and I take this and I plug it into the first one, notice the first one doesn't care about z. Now that we have z, that's nice and everything, but it only says take the x value, square that, take the y value, square that, sum those together, and you need to get 25. Not 25t, not something that changes with time. You need to get exclusively 25 no matter what the time is. And then the second equation says you need to take the x coordinate, whatever that is, in this case, 5 cosine t. You need to take the y coordinate, whatever that is. You need to multiply those together, and those have to equal your z coordinate. If they don't, then you're not on this second surface. So because this equation right here, this curve equation, satisfies both the cylinder and the surface equations, that's why it has to be on both, right? The curve of intersection is just literally the thing that's on both surfaces. Excellent. And then a question down here. So the question is, do you need to define the set of t, this domain, in order to get full points? No. So you need to make sure that you cover the entire curve of intersection, but the default is if you don't define your domain, that there's no restrictions on it, that t would actually range from negative infinity up until positive infinity. So in this case, you would just keep on going around that curve over and over and over again, but you would certainly hit every point at least once. You'd hit it infinitely many times. So as of right now, with curves of intersection, you don't have to specify the t values there. But again, later on, we're just kind of getting into some good habits for chapter 16. We're going to do things like around this curve here. We're going to integrate around this curve. And then it really matters. You want to hit each point once and only once. In fact, even now, I could ask you if I wanted to set up an arc length style question, right? Now that we have this curve of intersection, I could ask you, how long is that curve of intersection? And then you need to integrate, and you want to add up the length of the curve as you go around it once, but you don't want to go around it 5 times. Otherwise, it's going to be 5 times the answer, right? So you want to make sure that you hit every point once, but not more than that. So the 0 to 2 pi will become increasingly important. But not yet. Good. Any other questions here? Well then, why don't we go ahead and see what's next? Oh, sorry, up here, yeah. Yep. Yes. So yeah, the question is, in fact, another perfectly fine parameterization for this would be as you started to allude to, cosine of 2t and sine of 2t. You're now going around the circle essentially twice as fast, but you still go around the same circle and everything. And because these match, what's inside of the cosine is inside of the sine, everything will work out. Of course, you need to kind of continue this and sprinkle those along here. But now the range for t would be 0 to pi instead of 0 to 2 pi, because that's what it would take in order to go around the circle once. Yeah. So you're really thinking about the period of sines and cosines for this. All right, let's jump back here. And we did 8 and we did 6. So it looks like 7 and 10 are currently tied at 15 votes each. So why don't we do those, 7 and 10, and then we can come back here again. So 7, right in between here. This is finding an arc length function. So arc length functions starting at this base point. So this is something that got covered in the pre-class video for this section. This was really about the 13.3 is where the arc length stuff comes from. Again, the arc length function was defined in the pre-class video. And then unfortunately, we didn't get to the one problem that I had in our in-class notes that kind of covered this. We didn't quite make it to. So the solutions, again, are posted to D2L for that. But again, we'll go over this now. So arc length function, typically, I don't know, you can use like S of t or something like this. It's going to be basically our arc length stuff. So our good old arc length function looks like this. It's the integral of the magnitude of the derivative. And you need to know some starting and some ending point. So that's what normal arc length looks like in our class. And of course, we did that quite a bit in class for 13.3. The arc length function is pretty much the same thing, except for it doesn't give you an ending time. So it's basically just, it's going to give you a starting point or starting an A value, essentially, but it's not going to tell you where to end. Instead, your ending is going to be some variable. And so that's what you use t for here. So I'll use I guess I'll use A still here, but we'll have to figure out what that is. And then since t is going to be the variable that you use to say, this is when I'm stopping my integral, it's not really good practice to double use the same variable. And so quite often in these, we say, okay, well, instead of t there, I'm going to go ahead and use u. So I'll just use u's instead of t's. And again, this is how it's set up in the book. And I've basically followed suit. So that way, as you read the textbook and stuff like this, it's not different in class than it is in the textbook. So this is the setup here that we need to figure out. And that'll give us our arc length function S of t. But again, it's going to be a function. So we solve these very similar to how you solve just regular old arc length. So I'm going to need to find, maybe first off, before I start with my calculation, let me find r prime of u, and then I can do the magnitude of r prime of u, because that's the thing that I'm going to need to integrate. So again, we work kind of inside out. Next up after that, I'll integrate. That's even more outside, and then I'll plug in my values. So r prime of u. So I'm going to go ahead and take my derivative here. So the derivative of sine is going to be cosine. Leave the inside alone, then multiply by the derivative of the inside. So a small chain rule here. When I take the derivative of my second component, I got a cosine. So I'm going to have a negative sine. Leave the inside alone, then multiply by the derivative of the inside. The derivative of 2t is 2. And then finally, we have the derivative of 4t. That's just going to be 4. Now that's really technically r prime of t, right? I was using my variable t again, kind of because that's what I started with. But this is supposed to be r prime of u. So instead of t here, I should swap out, and everywhere I see a t, I should put u. Fine. Not that much more difficult, right? And now it's consistent with everything. Okay. Now, this is the thing that I need to find the magnitude of. So the magnitude, just like we did back in 12.2, you're going to take each component, square it. So let's see, 4 cosine squared of 2u Negative 2 squared is also going to be 4 sine squared of 2u. And then 4 squared is going to be 16. So again, square each piece, sum them together, throw them under a square root. That's the magnitude. Now this is the thing that we're about to integrate. And as we saw when integrating these things with square roots, it's nice if you can simplify them. And I notice that we have a cosine squared and a sine squared, right? And so if I go ahead and I factor out this 4 here from both of these, I'm going to have cosine squared plus sine squared. And again, literally anything can be in those sines and cosines. It's got to be the same thing, but it could be just t's, it can be 2u's, it can be 5 thetas. So long as it's the same in both of those, cosine squared plus sine squared is always equal to 1. Oops. So to get my arc length function, I need to integrate root 20 with respect to u, and then I'm going to plug in t as my variable, but I'm supposed to have some starting point, right? Some starting point here, and that should kind of correspond to this point up here. Oh, sorry, yeah, question. Yes, yep. Yeah, so cosine squared plus sine squared, t could be equal to 0, t could be equal to 5, t could be equal to pi over 3, t could be equal to anything. And you can verify this in your calculator too, right? So, I mean, if you ever get nervous on a quiz or an exam or something like this, and you start to question yourself a little bit, which happens to everyone, right? Plug it into your calculator. Cosine squared of 3 plus sine squared of 3. And your calculator will output 1 exactly, right? And then that'll be very, give you some good confidence. All right, so I'm just about ready to start, integrating and plugging these things in, but I need to know what this a value is, right? And so I know, and some problems are nicer, by the way. They'll say, starting from t equals 5 or something like this. They may just give you the starting value as a t value, in which case that's just your lower bound of the integral, and you're happy. But in this case, it gave us a point, right? And points, again, have x's, they have y's, and they have z's. They have the coordinates. And I want to know what time is associated with this point on my curve. So if I want to be at this point, I need that sine of 2t, that's my x coordinate for my curve, that should be equal to 0. But I also need, right, because I'm at the point, so the x value has to be the same, the y value has to be the same, so this means that cosine of 2t needs to equal 1. And we need that the z's are the same. 4t has to equal 4 pi. If all 3 of those things aren't true, then you're not at that point. You're someplace else, right? You need the x's to be the same, the y's to be the same, and the z's to be equal to the same thing. So of these 3 equations, 2 of them are kind of the wrong ones to look at, right? Because, for instance, there are infinitely many places where sine is 0. Sine is periodic. It's going to go back and forth. It's going to cross 0 many, many times. Sine of 0 is 0, right? Sine of pi is 0. Sine of negative 3 pi is 0. There are infinitely many places where sine is 0. Likewise, cosine is 1 many, many places. However, looking at this third one, there's only one place, only one time value, right, where 4t is going to be equal to 4 pi. And that's going to be when t is equal to pi. Of course, you could be paranoid, right? And you know that now if you set t equal to pi, that at least this works out. But does the first 2 actually work out, right? And you could plug this in and, right, you get sine of 2 pi, that equals 0, yes. And cosine of 2 pi, yes, that equals 1. So yes, when t is equal to pi, all 3 things are true. So the time value that's associated with this point, right? When am I at this point is when time is pi. So all this to say, right, my starting time is going to be pi. So again, starting from the point, 0, 1, and 4 pi. So the time that's associated with that point is pi. Okay, the rest of it's just pretty nice. When I integrate root 20, that's a constant. So when I integrate it, I'm just going to get x. Well, in this case, I guess I'm integrating with respect to u, so I guess technically u. And then I'm going to plug in from pi to t. So this is going to be root 20 t minus pi. And that is my arc length function. Again, it's a function. It relies on what t is. There should be t's in there. That's my arc length function. All right, we'll go back here and then up here. Yeah, so yeah, you need to evaluate out the integral. Yeah, typically for these things, evaluate out the integral. This comes from the definition. So the variable t is always in the upper bound. That's your ending time. And then the a, it turned out to be pi in this case, is always the starting. It's the lower bound, right? So the fact that it says starting from this point, if it said ending at that point, right, that would be the upper bound. But the starting from, and again, this is very consistent. This is how all these problems are typically worded. Yeah, here.
So because they only gave us a starting point, we have to make an endpoint a variable.
Yes, but that's also in the definition of the arc length function. So we could go back here really quick to the video, since there's been a few questions about this. So here's where we were talking about arc length. And then this right here, yeah, is the arc length function with a base point A, right? So that base point was what, the 0, 1, 4 pi in our case, right? But notice that t is always the upper bound, right? And there's always a variable in here. So yeah, for the arc length function, that's always the case. Good. Any other questions? All right. Well, I think we have time for also what, number 10 as well. So let me go to number 10. So number 10, yeah, I wanted to include some true false. Some people tell me that the true false, right, they're typically a bit more conceptual, that sometimes these are most difficult. It says, suppose that for a point in spherical coordinates, we have that theta is in the range somewhere between pi over 6 and pi over 3, right? So I guess first of all, for this, anytime, right, spherical, we only saw spherical stuff in 13.9. So if you wanted to review and think about more spherical style problems, right, you'd be thinking about this last section that we did in Monday's class. 13.9 is what I called it. That was the introduction to cylindrical and spherical stuff. So we know that theta is somewhere between pi over 6 and pi over 3. And then the true false part is, right, then we know the point must lie in the first octant. Okay. So there's a couple different ways that we can think about this, right? First of all, we need to remember what the first octant is. The first octant means that x should be greater than 0, y should be greater than 0, and z should be greater than 0. The only octant that has a name, first octant. There isn't a second octant or a third octant, as you probably recall from 12.1. But first octant is kind of like the first quadrant, but in 3D, right? So it's where everything's nice and positive. Now, we're given some information that theta must range between pi over 6 and pi over 3. So if I was thinking about this, and again, kind of graphing things in 3D is difficult. Whenever possible, I like to start graphing things in 2D, right? So theta is the same theta from cylindrical, and it's the same theta from polar, right? So theta is just the classic theta that we know and love. So if you put this in the XY plane, pi over 6 is 30 degrees, and pi over 3 is 60 degrees, right? So it needs to lie somewhere over here. Somewhere between the 30-degree angle and the 60-degree angle. Again, the thetas always come off the positive x-axis. So here's the pi over 6, and there's our pi over 3. So somewhere in that green shaded area, we know theta must live. So that guarantees, right, if we're somewhere out here, and I don't have any more information to go off of, but if we're somewhere in this wedge, I know at least that my x is positive, and I know that my y is positive. I know that for sure. The question is, do I know my z is positive? And again, there's no more information to go off of. Theta only talks about as we go around the z-axis. If I wanted to influence my z value, I need to be able to talk about my up-down angle. My up-down angle was phi, right? So phi equals 0 is pointing straight up. Phi equals pi is pointing straight down. I would need to make sure that I'm at least above the 90-degree mark, right? If I was at least, from 0 to pi over 2 or something like this, I'd be pointing up. And then I'd be happy. I could guarantee that my z's are positive. But as of right now, my phi could be, pointing us down here. We could have a negative z value. So do we know that it must be in the first octant? No, we don't, right? So the answer here is false. And so in particular, right, you can come up with many different counterexamples, but if rho equals 1, theta equals pi over 4, and phi is equal to 3 pi over 4, this satisfies the theta condition. And yet, if you were to plug this in and figure out what x, y, and z are, you'll see that z is negative, right? And so sadly, this can't be true. So you need more conditions added to this in order for it to possibly be the case. And now that you kind of see how you think about this sort of problem, you can kind of get there a little bit faster, that just theta only tells you about the XY stuff. It only tells you left and right. It doesn't tell you anything about up and down. So there's no reason that z has to be positive. So it must be false. Yeah. Can I? Yeah. Sure. So here's x. I probably have chosen a bad maybe viewpoint here. But so this would be maybe my 30 degrees off the positive x-axis. Here would be my 60 degrees off the positive x-axis. So these go on forever. Again, there are no restrictions on rho here whatsoever. And there's no restrictions on phi, kind of the up and down stuff. So these are going to be kind of these half planes. So you're going to be inside of this wedge here. But notice that not only do you get some points that are in the first octant above the xy plane, but you also get points that are down here below the xy plane. And those are the points that are the issue. So, but yeah, you're going to be inside of this wedge here between these two planes because there were no restrictions on z values. So somewhere in this wedge here is where points that satisfy theta values between pi over 6 and pi over 3 must live. We'll go here and then here. Yeah. Yeah, the question is, what is the range for phi, right? So theta ranges from 0 to 2 pi because you need to go all the way around, right? Phi only ranges from 0 to pi because you need to be able to go from straight up to straight down in order to get all of the points. The theta is going to take, right, if I wanted to get a point behind me, I'm not going to let phi keep on going and try to get the point that way. I'm going to turn around, right, using my thetas to get that point. If you allow phi to range instead of from 0 to pi, if you do from 0 to 2 pi, what you're going to do is you're going to get all of your points twice, which again, maybe right now is not the biggest thing in the world, but when we start calculating out volumes of things and we do triple integrals and that sort of stuff, if you start double counting your points, you're not going to get the volume, you're going to get 2 times the volume, right? So it matters later on especially. So that's why restricting your phi and just always having, I mean, in this class, rho always being positive is just something you should have. Likewise, phi ranging from 0 to pi is just always kind of a given. Theta ranging from 0 to 2 pi, just make that your givens, and you can solve every single problem in this class with those conditions. One more time. Yep, phi equals 0 points straight up. Down here.
Like on some concept questions on the quiz,
Huh?
it was like true, false, or not enough information given.
Okay.
If we were given like those 3 options for this question, we have to pick not enough information, or should we pick false for that? Like, do you get what I'm trying to say?
Yeah, so the question is, if you have a third option where the answer is not enough information is given, I would say that a problem like this isn't really well suited for this, right? And so, if someone, because we have kind of a team of instructors who writes these things and, we're given opportunities to object if we don't like the way that something's worded, or if it's like too confusing, or if it's not consistent enough with like web work and things like this, right? Because everyone does the web work problems, but not every person sees my videos or comes to my class, sort of deal. There are other instructors. And so, you know, I would have an opportunity to object to such a thing, right? Because I think that would be a little bit confusing, because you're right. When you have a mathematical statement, it's either true or false, right? So to add a third category of not enough information is given, it's really then you're taking away, false doesn't no longer make sense, because yeah, if you come up with enough additional restrictions, you probably can make any statement true, right? For instance, if I say, instead of all of space, we're only going to talk about the point x equals 0, y equals 0, z equals 0, or something like this, like you can make almost anything true. So not enough information given is kind of a silly, I would have issue with that question.
I mean, I'm gonna assume it's just true and false, but like, I
Yeah.
vaguely remember on the quiz, I think there was like a question or two that said not enough information given for like concept one. I could be wrong on that though. I could just be like,
Yeah, I mean, I'm not saying that there are no questions out there for which those three options I would object to. But a question like this right here, I would object to that.
okay. So like questions like these are more like 99% are gonna be like true and false, right? Like you're only gonna be.
Yeah, because it's either always true or it's false, right? It's not true all the time. I saw a hand over here. Mhm. Yeah, this is, you're really getting into the weeds here. But yes, if you wanted to hit, there are different ways that you could hit every point once and only once. You don't have to do theta equals 0 to 2 pi. You could do theta equals 2 pi to 4 pi, right? You could do all sorts of fun things. And so yes, if you insist that you really want your fees to range from 0 to 2 pi, there are ways to do this. But yeah, again, you're probably making life a little bit harder for yourself than it needs to be. But yes, it's technically correct. I think I saw your hand next, and then we'll go here.
But it's phi instead of theta.
If it was phi instead of theta, you could no longer say anything about x and y. Basically, you're going to be between two cones. So I know that my phis would be between 30 degrees off the positive z-axis and 60 degrees off the positive z-axis, but I don't know where I'm pointing this, right? Because although my hand's stuck and my vertical angle is now fixed, it's somewhere in here, I don't know if I'm putting now with my correct thetas, right? I would need to restrict thetas in the first quadrant, right? As soon as I let theta be equal to pi, then that would be a problem. Yep. I'm going to stop the video here because I feel like we are getting on to some one-on-one questions and whatnot, and I'll call on the people back there. But yeah, good luck everyone on the test, and I'll see you Friday for new math.